Okay, same question, but now doing a decreasing time schedule algorithm. And the whole point of this is those that were in tune with me in the notes that were actually here, because I didn't make that video. Too bad you don't always get videos in life, I guess. That's a nice little added feature that Mr. S offers. But when we talked about the last example in 7.2, we talked about just verbalizing, reversing it. I think we did decreasing time first, and I wrote that down. And then we talked about increasing time, actually being better, less idle time, and actually done quicker. So we're going to see what happens when we try doing a decreasing time schedule algorithm, and then see what the result is. With that being done, first you should have in mind what would the total, if there was one processor, time be. That's the maximum this project would take if there was only one person. The critical time, again, is the path, the maximal path that has the highest number. The reason we care about that is the minimum time this task could get done. So again, I don't care if there was a million processors. This path right here can only be done this fast no matter what, because each task would have to be done before the next one. And two processors working on task 4 would still take 11 minutes in theory of this section. So having those in mind, I think it's a good idea to get a little scale going so that we start assigning the tasks. We have a relative situation going on. So processor 1, sync this down a little bit, processor 2, and now doing a decreasing time algorithm, we have to find or assign the largest available task. Again, if you watched the first video, you should know what that means. It starts with the sources. So processor 1 gets task 1 because it's the largest available task. Don't I sound wonderful? I put a 20 up there. It's smart to put these numbers. Maybe I've been putting checks. Maybe cross it off. Well, I'll check it. And then understand that this is an action but not complete. Right? So we're assigning a task to processor 2, and then we'll see what happens from there. The next highest task is T9, and that is 16 minutes. So relative to that one, we want to put it like this. Probably went a little too far, but that's fine. T9, sorry. And that's 16 minutes. All right. So now, who's open? Well, processor 1's still working on task 1 when processor 2 gets done with task 9. So it's processor 2 that will go. Now what I do, I think it's smart to do this, is to do this to say that this is done now, which may open this up, but it doesn't open up task 8 because task 8 has 2 other precedence relationships. So that's not an open task. And task 2 is not open yet because processor 1 is still working on task 1. So at about 60 minutes, we're only right there, not open. So the only available tasks are 7 and 4. So processor 2 must work on task 7, the larger of the 2 remaining. I'm trying to do the math. 31, I think, 15 plus 16. So I want to try to make 31 happen. That looks like right around 31. Sounding better and better. I should just whisper. Maybe I'll just do that. And then maybe you can hear me still because this is a high-def video. So that's 15 minutes. 15 plus 16 is 31. There's 31 on the scale. So now I've done task 7. And task 7's going, oh, task 1's complete now. See, task 1's complete right here. So now I've opened up task 2. And now processor is idle. Not idle, but ready for a task if one's available. And there's 2 available now. Task 4 and task 2. This is the decreasing time algorithm. So since, let me pause for a second. Since processor 1 is available to work and task 2 is larger than task 4, the decreasing time algorithm says I should work on task Okay, so I put that here. Or task 2, I meant. Which is 12 minutes, which gets us right around 32. Not right around, right at 32. So this is task 2 being done. Now, task 2 gets started. And this is 12 minutes. So now, task or processor 2 is now open after 31 minutes, and this one's done in 32, so they're ready. So they have to be assigned the next available task. Now this isn't quite done before processor 2 is available. So now they're stuck with being assigned the only available task at this point, which is task 4. So this is 11 plus 31, which is 42, I hope. All right, and then that means task 4 is done right now. So task 4 is done, checked it off. Task 2 is checked off down here. I just didn't like where I put it. Okay, well, during the assignment of task 4, task 2 gets complete. So now we can assign task 3 the only available task because task 4 is in action. But it's, this processor is available while task 4 is being done. So 5 isn't open. So there's only one task open for processor 1, which is task 3. So task 3, this is 32 plus 9 is 41. And I believe this was at 42. I didn't put T4 down here, which should have been done. Yeah, this was at 42, and I might want to mark that at this point. And this is at 41. So these are real tight right now. And that was task 3, which was 9 minutes. So these are real tight. This is kind of tough. You got to really be good with this as far as who's ready and who's not ready when they're really this close. This ended up at 41 minutes when we just add these numbers up. And I should have added these up at some point and know who was ready and who was done. But as you see this in action, you should understand how these get assigned. So now what's interesting is T4 is getting done. T3 is done while T4 has 1 minute left. So you might think, okay, fine. Since T3 is done, we can move on to T8. But T8 has a precedence relationship. They'd have to have T6 done before we could do T8. Easy for me to say. So now we have to wait, and there's this little bit of idle time, which is only 1 minute, where processor 1 has to wait for T4 to be done. All right, so now at this point, this is where something interesting happens. Somebody would have to do T5, and then no one can work on T6 before T5 is done. And then somebody, this has been completed previous, I didn't finish this line. Now that these both are done, then someone would have to work on this. And then someone would have to work on either this one and wait for that to be done before this one could be done in order to get T8 done. So it's kind of weird what happens here. And I'm going to back up and show you how we assign that here. So where I confused myself was I didn't mark this as done. T3 is done right here, so I complete this line. T7, T4, 1, 2, and 9 are all done as shown in this graph. So now what we have is only one available task. So I can't assign a processor on this one or this one because you can see this all has to be done in order. So unfortunately, what has to happen at this point is I have to do task 5. I have to wait for task 5 to do task 6. And I have to wait for task 6 before I can do task 8. At this point, I couldn't care less who you assign this to. The key in the book you see assigns it to the top. You could just as easily assign this to the bottom processor. I don't think it really matters. So, sorry. 42 plus 17 is 52, 59. I'm going to go ahead and do what, giving it to the first processor. Again, it doesn't matter. So I'm at 59. Might be a good idea to keep track of these. I guess you could assign this to this person next. It doesn't really matter if you want to switch off. If this was, okay, I'll do task 5, then you do task Well, for the purpose of getting your homework done, just keep it with the same person. This is 22, 59, 69, 79, 81. So now I'm at 81 when I do task 6. And then 81 plus 35. Oh, dear goodness. I can't think. 116. Genius, Mr. I never was good at math. Put that on Twitter. See, my math teacher even admits he wasn't good at math. All right, 35 minutes there. That's 116 total. Okay, so now let's look at the two things before we finish this off. Doing this two different ways. It's all gone. I erased it. Sorry. This ended up being the better of the two options. Doing the increasing time scheduling algorithm. That's the point. You choose one way, you choose the other. One may be more efficient. I think if my memory is correct, and you just have to go through your memory of being in class, it was reversed in the example that I did in 7.2 last week. So anywho, that's what we end up getting. Of course, you can just check the key for the answers anyway. The point of the video is to see this done in action. So is the schedule optimal? Optimal? Heck no. No, because, and I'm just going to verbalize it. You'd have to write this if you were a good student. No, because this is much larger than the critical time. Only an optimal schedule would be such that the Gantt chart ends up equaling what the critical time would be. Blah, 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 blah. For how much time are the processors idle? Unfortunately, it's quite a bit. It's 1 minute here, so we got 1 minute. And then it's the 17, the 22, and the 35 hike. All those added together, which you'll learn how to add those numbers in calculus. I'm kidding. You can add those numbers, and that's the idle time. I'm done. Sorry for my voice and everything.